Hi students. In this video segment, I'd like to take a look at section 4.5. In this section, I would like to look at some applications of higher order differential equations. Actually, that's the title of the section. I'd like to look at one application for us. The main idea in this segment is to consider a spring hanging vertically, say a spring hanging from the ceiling, attaching a mass to the spring, getting that spring in motion, and then finding an equation that gives the position of the mass as a function of time. Okay. In order to do this, we need to use some concepts from physics. So I'd like you to try as best to follow along with the derivation of the differential equation using a couple of things from physics, namely Hooke's law and Newton's second law of motion. But if you're unfamiliar with those things, don't worry about it. The bottom line is that we're going to develop a specific initial value problem for all the cases that may arise. And you can use that initial value problem, the differential equation and initial conditions, to solve spring motion problems, regardless of whether you've had physics or not. Okay, so let's start with a reference frame. By a reference frame, I mean let's start with a vertical axis to keep track of the position of the spring. I'm going to use the same notation as our textbook, and I'm going to orient the axis the same way your author does. So we're going to consider a sort of y-axis, but we're going to call it the u-axis, and we're going to call the positive direction downward. This decision to call the positive direction downward is purely arbitrary. I've seen textbooks go both ways. That is, some textbooks will call the positive direction downward, some positive direction upward. I don't think it really matters much. So let's define this thing called the u-axis with the positive direction being downward. Okay, and I haven't located where I want to call 0. We'll do that in a second. I'm going to need a little more room between my title here. Let's see if I can do this. Oops. Sort of. Hang on. I didn't account for enough space here. This will work. Okay, I think we're set now. Okay, so right next to the u-axis in my little picture here, I'm going to draw a picture of the spring attached to the ceiling. So here's you can imagine this little line is the ceiling, and I'm going to put the spring, attach the spring to the ceiling. And here's my little picture of a spring. It only has 3 coils on it. Here's our spring with no mass attached to it. Okay. Right next to that is where things start to get a little more interesting. What I want to do is I want to imagine attaching a spring to the a mass to the end of my spring, a mass of say m kilograms, and we'll designate the mass with the small letter m. Okay, so I'm gonna attach a mass to the spring, and that's going to stretch out the coils. So here's the coils. Oh, my terrible drawing again. Stretched out a little bit. Okay, and here's the mass m. Okay, so we'll label it m, and that m happens to be its mass also, m kilograms. Okay, we're gonna designate that position as u equals 0. So that position right there, that's going to correspond to u equals 0. Okay, and I'm going to continue this little line this way for reasons that will become clear in a little bit. And let's assume that by attaching the mass at that point, that we've stretched the spring from its natural position by a length of capital L. Okay, so let's say this distance is capital L. Okay, now what I want to do is I want to apply Newton's second law to the mass. In terms of, in physics lingo, what I'd like to construct is a free body diagram on the mass. So a free body diagram just lists all the forces acting on the mass. So let's do that. The first force that's acting on the mass, which is kind of obvious, probably whether you've had physics or not, is the gravitational force. So let's call that force due to gravity, let's call it FGR. Okay. The spring doesn't want to let go of the mass. If it could think, I guess it wouldn't be wanting to let go of the mass. So the spring is exerting a force in the opposite direction that the gravity is exerting the force on the spring, on the mass. And we'll call that FSP for force due to the spring. Okay, so what I'd like to do is use Newton's second law to write a relationship between these two forces. First, the force due to gravity is equal to the mass of the spring times the gravitational constant. In the metric system, the gravitational constant is approximately 9.8. Your author uses 10. He rounds this up to 10, which for me seems a little strange. In every physics course I've ever looked at, the gravitational constant was either 32 or 9.8 in the metric system. We'll use his value of 10. Okay, the force that the spring exerts on the mass has been determined, or is determined experimentally by Hooke's law, and it is minus k times the length L that the spring is pulled from equilibrium. This is called Hooke's law again. Hooke's law. The K is called the spring constant. So it depends on how loose or how tight the spring is, how thick the materials used, the metal used to make the spring are, etc. So a slinky will have a very different K, spring constant, than, let's say, the shock on a car, a shock on a car. Okay, I guess I'm using kind of extreme examples there. Okay. All right. The minus in this is mostly psychological. It's to indicate that the spring is pulling in the opposite direction as gravity. I've seen where the force through the spring is written as KL, where K turns out to be some negative number. So we'll just use your author's convention of putting a minus sign in there. So the spring force is minus KL, where K is a spring constant. K is a positive number. Okay. So let's apply Newton's second law to the mass. Newton's law says that when you add up the forces acting on the object, force due to gravity plus force of the spring on the mass, that equals the mass times the acceleration of the object. So this equals the mass times the acceleration of the object. Now the idea in attaching the mass and stretching the spring out this distance L from equilibrium, and I guess I didn't name the term equilibrium yet, the stretching the spring by L, is that we've brought the spring to rest. So if the spring is if the mass is at rest at this point, then the mass is not accelerating. So the mass times the acceleration will be 0. And I guess I should reverse engineer that term I just used. When we've done this, the position u equals 0 is called equilibrium. I don't think I said that. Equilibrium. I don't think I said it before I used the term in a sentence here. So okay, so let's continue this free body diagram. Let's put in the quantities. The force due to gravity is mass times gravitational constant mg plus the force due to the spring, so minus KL equals 0. This allows us to solve for the spring constant for our particular spring. So the spring constant then will be mg over L. And different springs of different stiffness, etc., will have different spring constants. Okay, I'll identify that as a spring constant. Spring constant. Okay, so let's go back up to our diagram. And let's change things up again. Let's make things much more interesting. Now that we have the spring in equilibrium, let's imagine that we physically take the mass and pull it down or push it up from equilibrium. Doesn't make any difference. In the diagram, I'll show us pulling it down. Let's pull it down from equilibrium and get the spring in motion. And the idea for us in this section is to find a differential equation that governs the motion so that ultimately we can possibly solve the differential equation for the position of the spring u as a function of t. So let's do that. So coming over here again, here's our next situation is, let's just say at the mass put into motion. Put into motion. And what do I mean by that? What I mean is we're going to take the spring at time t equals 0 and pull it down or push it up. But we'll say pull it down. Pull it down by u sub 0. And then we'll either release it, in which case its initial velocity will be 0, or we'll help it out a little bit. So let's assume that we're helping it out a little bit. We've pulled it down by u sub 0, and we've given the spring, we'll give the spring an additional nudge with a velocity of u1. So this definitely gets the spring in motion. Let's draw the spring actually in motion now. So here's the spring. If it's pulled down a bit, it's now going to be below equilibrium. It's actually going to move up and down past equilibrium. Let's assume that at some particular moment in time, the spring is some distance or some displacement u from equilibrium. So in this case, I've shown u to be some positive number. Spring goes up and down and up and down. So the spring goes from positive to negative through 0, etc., etc., etc. Okay, so now let's draw a free body diagram of all the forces that we want to have acting on this spring. Okay, so what I'm going to do is I'm going to draw all the forces acting on this thing. Let's say we again look at the obvious force is the force due to gravity. So F gravity's still pulling down on us. Let's say that we also have the spring attempting to get itself back into equilibrium. The spring is going to be pulling against the force due to gravity. So here's the force due to the spring on the mass. Let's introduce some more realistic forces. This mass need not be sitting in a vacuum. This mass could be underwater. It could be in air, or it could be in a tank filled with oil. And in all three of those situations, water, air, or tank filled with oil, we will have a resistive force on the spring due to those three things. So unless we're in a vacuum, unless we're in the vacuum of space with this spring, then we're going to have a frictional force acting on the spring. Let's draw the frictional force upward. Why upward? Well, why not? it will act downward when the spring is moving in the upward direction, and upward when the spring is moving in the downward direction. Let's see if I got that right. If the spring is moving upward, oh yeah, so the frictional force will act opposite motion. So let's assume at this moment, just for the heck of it, that the spring is on its way up. Down rather. If the spring is on its way down, then the friction will be acting upward. I think I'm obsessing too much about this. So let's call this the frictional force on the mass due to whatever medium we're in, whether we're in water, air, oil, or whatever. Okay. Let's also assume that we have potentially one more force acting on this. Let's assume that we can stick our hands into this situation and help the spring along in different directions. Let's assume that we can also have an external force applied to the spring. F external force. So reaching in from the outside, something independent of this system, independent of the friction, the spring force, or the gravity. We apply just an arbitrary force helping this spring out as a function of time. Okay. So let's give those quantities, at least as many of them as we can, some actual amounts. So the force due to gravity doesn't change. The force due to gravity is still a constant mass times gravitational constant. The force that the spring exerts on the mass has the same form due to Hooke's law. It's the spring negative spring constant times the distance that the mass is away from its natural length. Okay, before, when we were considering the equilibrium position, the spring was L units away from its natural length. Now the spring, according to my picture here, since the spring is below equilibrium, the spring will be that L plus an additional U away from its natural position. Again, U is varying with time, so U can be 0, you could be positive, U could be negative. Okay, the frictional force we're going to borrow from experimental physics. So F friction. Apparently, and I say that because I'm a mathematician and not a physicist, apparently it's very common to model the frictional force as being some constant multiple of a simple power of velocity, or using the terms of linear algebra, it's very common for the friction to be directly proportional to either velocity or a simple power of velocity. Let's say that the frictional force is some constant, and this constant F is not a function. Your author uses this F, this small f for the constant, some constant multiple of velocity. So let's say that the frictional force is minus some constant times velocity. Why minus? Purely for psychological reason for right now. Just like the minus in the Hooke's law, the frictional force acts in the opposite direction of motion. So if this thing is moving downward, then the the velocity will be positive. Remember, calling positive downward, so the frictional force will be negative, and vice versa. If the spring is moving upward, or if the mass is moving upward, velocity will be negative, frictional force will be positive, acting downward. So things work out with the sign this way. So we can actually do one more thing with that frictional force. See, velocity is the time derivative of position. So we could write this frictional force as minus F u prime, where prime is derivative with respect to t. And finally, we have an external force. Let's say F ex for external force. And that can be some function h of t. Okay, and that's about the best we can do for the external force, since we're not looking at a common force for the external force, such as friction, or one from the Hooke's law, due to Hooke's law for the spring and so forth. Okay, let's construct a free body diagram for the spring in motion now. I want to move something out of my way. So there we are. I'm going to say if my surface will allow me to, and it did, I'll move the spring constant over. Okay, so let's construct a free body diagram on the spring at this time. So we have the force due to, using Newton's second law, we have the force due to gravity plus the force due to the spring, the spring acting on the mass. We have the frictional force. We have the external force, and that's all we're accounting for in our diagram. And that, according to Newton's law, is mass times the acceleration of the spring. Okay, now let's put the quantities in that we know. The force due to gravity is mass times gravitational constant. The force due to the spring, so plus the force due to the spring, so minus K times U plus L, plus the frictional force, so minus F U prime, plus the external force, the only other force in our system here, equals the mass times the acceleration. Now, acceleration, remember, is the second time derivative of position. Okay, so without any simplification, there's our differential equation. But there's a little bit of magic that happens with this differential equation. Let's concentrate on the first two terms here. A little bit of magic happens, and for that magic, I'll change pen colors so you can kind of keep the magic separate from the equation. So let's expand the second term there. So we have mg minus ku minus kl. Let me make my pen a little finer. And I'm going to rearrange those three terms. So we're looking at mg minus kl minus ku. And I want to lump the first two terms together. I want to group those first two terms together. Do those first two terms look familiar to you? Well, look to the left and up just a little bit. And in our free body diagram for the spring in equilibrium, we have that term, that mg minus kl, occurring. Let's see if I can change it to blue. We have it occurring there, and that quantity, mg minus kl, is 0. So what we get is 0 minus ku, or minus ku. So our differential equation becomes a little easier on the eyes. So back to green here. So that the first two terms, mg minus k times the quantity u plus l, simplify to minus ku minus fu prime plus external force h of t equals mu double prime. Let's take that differential equation and rewrite it in a way that we're kind of used to looking at our second order differential equations or nth order differential equations. Let's look at let's take the differential equation and write it in terms of decreasing order of derivatives. And I'm going to come back to my normal colored for the pen here to do that. So we're looking at mu double prime plus fu prime. If I gather the terms with the position function u to one side, plus ku, and keep the forcing function on its own side. Here is our differential equation. And remember, this differential equation comes with it. What comes with it are two initial conditions where we've imagined that we've pulled the spring down a little bit past equilibrium initially, or pushed it up, depending on whether U sub 0 is positive or negative. And we've helped it along with a single nudge at time equals 0. So we've given it an initial velocity. Together, we have an initial value problem governing spring motion. This is real world math going on here. This is amazing. Look at how simple this differential equation is. It's such a simple differential equation, okay? And a simple initial value problem. Okay. To end this session, I want to solve a problem from your textbook. But before we do that, I want to mention a couple of items that your author brings up. I think they're kind of important items, so I want to bring them up here. If the frictional force is 0, okay, that is if this is is just done in a vacuum, then we have an undamped system. Then the system is said to be undamped. Okay. If the frictional force is not equal to 0, then the system is called damped. The system is damped. Okay. So with that, let's take a look at a specific example. All right, students. I've taken the liberty of pausing the video to write out the examples so that you don't have to watch me write out every single word. The example I chose corresponds to number 6 in your textbook. I've written the example in slightly different words, just so that we can kind of tear the problem apart bit by bit. Okay, so here's our situation. A 5 kilogram mass stretches a spring 25 centimeters. Okay, so that puts our spring into equilibrium. The mass is hung vertically then in a tank filled with oil, offering a resistance of 40 kilograms per second. The units look real funny here, but they're kind of needed, and I'll explain that in a bit. The object is pulled an additional 25 centimeters from rest. This is where we put the object in motion, and also given a initial velocity of 50 centimeters per second. Determine the motion, that is, determine the position of the object as a function of time. Okay, so let's start from the beginning here. We have a differential equation that we looked at a few seconds ago. The differential equation has 3 quantities on the left-hand side that need to be accounted for. Let me see if I can highlight those 3 quantities. The differential equation on the left-hand side has 3 quantities, m, f, and k, on the left-hand side that need to be accounted for here. So let's, we know what m is. M is 5 kilograms. What we need are k and f. So the spring constant, to find the spring constant, remember physically what we're doing is we're imagining taking the spring and attaching a mass to the spring, and that pulls the spring a certain amount, capital L. It was in our drawing or our work above. So the distance is L to bring the spring, too much coffee, to equilibrium. And we determined that the spring constant then has a value of mg over L. Okay, so for our spring, L is 25 centimeters, and M is 5 kilograms, and G we're going to round to 10. That G, the units of G, are in meters per square second. It's the acceleration due to gravity, approximately. And we have a little bit of a problem with units. The length is given in centimeters, and the gravitational constant has units of length in meters. So we need to convert one constant to we need to have our constants in this using the same units of measurement. Okay, so I'm going to convert the 25 centimeters to a fraction of a meter. So there are 100 centimeters in a meter. So we have 25 centimeters is 25 1/100ths of a meter, or 1/4 of a meter. Okay. So the gravitational constant for our spring, not the gravitational constant, the spring constant for our spring is mg over L, m, g approximately 10 over L, and this is 200. Okay, and we can be a little silent on the units there. The other two constants we need are m, well, we already have that, that's 5, and F, the constant due to the frictional force. Remember, in our derivation, the frictional force is minus Fv, and they told us that the mass is hung vertically with a tank filled with oil, offering a resistance. So that they're giving us the value of F, the resistance of 40 kilograms per second. So for us, that F is equal to 40. And I mentioned that I would discuss why the units are the way they are. Well, the force is in newtons, or kilograms meters per second squared. So force is in newtons, or kilograms meters per second squared, per square second. And our velocity, concentrate on the expression for the frictional force. The velocity has units meters per second. So the velocity has units of meters per second. We need another unit of second in the denominator, and we need kilograms in the numerator. In order to do that, we're going to have our frictional constant in units of kilogram to get the kilograms upstairs in the numerator, and an additional per second so that we get per square second for force. Okay. Okay, so we have our frictional constant then. F must be 40. K is 200. M is 5, and we're ready to put those constants into our differential equation. So our differential equation from above was mu double prime plus fu prime plus k times u equals h of t. So m is 5, so 5u double prime. F is 40 plus 40u prime. K is 200 plus 200u equals, and we don't have any external force acting on the system, so equals 0. We also have a couple of initial conditions here. We have that the initial displacement was an additional 25 centimeters. Not the original 25 centimeters that brought the spring to equilibrium, but after that occurred, we pulled the spring an additional 25 centimeters from rest, and we gave it an initial velocity of 50 centimeters per second. 50 centimeters per second. Now we have to clean up these units too. Our units of length need to be consistent. So 25 centimeters is 1/4 of a meter. 50 centimeters is 1/2 of a meter. So the initial velocity will be 1/2 meter per second. Okay. So we have our initial value problem, the differential equation plus the two initial conditions, and we're going to take that initial value problem, which I'm going to highlight now in a nice blue, and we're going to solve it. Okay. Let's solve the differential equation first. Notice that we have a greatest common factor of the coefficients on the left-hand side. So let's imagine factoring out a 5 from the three terms on the left-hand side and then divide both sides by 5. If we do that, we'll get a nice u double prime plus 8u prime plus 40. 5 goes into 240 times. U equals 0. Now we're back into section 4.2 territory. Let's write out an auxiliary equation. The auxiliary equation would be lambda squared plus 8 lambda plus 40 equals 0. It looks like it wants to factor. It's not going to factor real nicely. So what we'll do is we'll use the quadratic formula. Quadratic formula says that the roots are negative 8 plus or minus the square root of 8 squared, sort of the b squared, minus 4a, a is 1, c, constant coefficient 40, all over 2a. So let's simplify these roots. This is negative 8 plus or minus the square root of 64 minus 160 all over 2. Or negative 8 plus or minus the square root of negative 96 over 2. 96 is 16 times 6. 16 times 6. And the square root of 16 is 4. So plus or minus 4i times the square root of 6. I because we're looking at a square root of a negative number. So this is a complex number. Or negative 4 plus or minus 2i times the square root of 6. So since the roots of our auxiliary equation are complex, we're going to get sines and cosines out of this, which is no big surprise. Since we have a spring that's bobbing up and down, we expect some sort of periodic contribution from sines and cosines. So we go directly to u. The real part says that we get the exponential e to the minus 4t. Remember, our independent variable is time and not x, so e to the minus 4t. The imaginary part gives us our sines and cosines, so times c1 cosine 2 radical 6t plus c2 sine 2 radical 6t. Okay. Well, there's a solution to the differential equation. Now let's determine the constants c1 and c2, and then we're done. A little bit of work to do. The initial conditions one of them involves a derivative, so we're going to need to take the derivative of this guy. In fact, I think we'll do it now. So let's take a derivative. We're going to need it anyway. So u prime equals, I have the product of two functions, e to the minus 4t and the linear combinations of sines and cosines of 2 radical 6t. So let's use the product rule on this. One version of the product rule says the derivative of the first function, so minus 4 e to the minus 4t, times the second function left alone, c1 cosine 2 radical 6t plus c2 sine 2 radical 6t. So there's the derivative of the first times the second, plus the first function, let me see if I can squeeze it in on the right, plus the first function, e to the minus 4t times the derivative of the second. Yeah, I'm going to be able to squeeze that in. So the derivative of the second, the derivative of cosine of 2, excuse me on that, cosine of 2 radical 6t is minus sine of 2 radical 6t times 2 radical 6 by the chain rule. So minus 2 radical 6 c1 sine of 2 radical 6t plus 2 radical 6 c2 times cosine of 2 radical 6 t. All right, kind of a long derivative there. Now, I'm not gonna simplify that derivative, and I'll show you why. Let's see if I can get rid of this little plus sign first. I might be stuck with that plus sign. Oops. I might be stuck with that plus sign for the rest of time here. There we are. That's why my videos are so long. Okay, let's apply the initial conditions, and let's not simplify that u prime. So u of 0 equals 1/4. U of 0 equals 1/4. So u of 0 equals 1/4. What does that give us? It gives us that 1/4 should equal, back to the original function, e to the 0 is 1. The sine of 0, when I substitute t equals 0 into the sine is 0, that gives me my first constant is 1/4. So c1 is 1/4. Okay, so now you're going to see why I didn't want to simplify my u prime. U prime of 0 is, what was it? I think it's 1/2. Yeah, 1/2. And here's the reason why I didn't simplify my u prime. Into my u prime goes t equals 0, and the u prime has a bunch of signs in it, and the sine of 0 is 0. So rather than simplify algebraically the u prime, I decided to just leave it the way it was, because the signs are all going to disappear. The cosines are going to go to 1, and the resulting equation is pretty simple without simplifying algebraically first. So u prime equals 1/2 when t equals 0, e to the 0 is 1, so I get that -4. I'm concentrating on u prime, and in the first set of parentheses, cosine of 0 is 1, so -4 times c1, the sine of 0 is 0, plus, now we're in the second major term in u prime, t equal to 0, e to the 0 is 1 again, sine of 0 is 0. The only thing I'm going to get from this is an additional 2 radical 6 c2 from the cosine term, and cosine of 0 is 1. Wasn't that kind of easy compared to simplifying algebraically first? Okay, well, we know that c1 is 1/4, so let's find c2. If c1 is 1/4, I substitute c1 into the second equation, plus 2 radical 6 c2. So 1/2 equals -1 plus 2 radical 6 c2. So adding 1 to both sides, I get 3/2 equals 2 radical 6 c2. So that tells me that c2 should equal 3 over 4 radical 6. If I rationalize the denominator, I get 3 radical 6. Radical 6 times itself is 6, times 4 is 24. Final value of c2, like a game show host right there. Final value, radical 6 over 8. So let's write out our solution and end this video. So the solution is u equals e to the minus 4t times c1. c1 was 1/4, so 1/4 cosine of 2 radical 6t plus c2 radical 6 over 8 times sine of 2 radical 6 t. Maybe the last thing to notice is, with all this friction acting, with all these forces acting on the spring, gravitational force, in particular the frictional force, the frictional force on this thing, we expect the object to actually slow down over time and approach the equilibrium position u equals 0. We have this object. It's sitting in oil. Then oil is going to continuously slow this thing down or attempt to stop this thing. So we expect that u should approach 0 as t goes to infinity, and it does. Within the parentheses, we have sines and cosines, which are just going to produce periodic motion without the e to the minus 4t, but that e to the minus 4t hammers u down to 0 through time. So this spring will approach equilibrium as t goes to infinity. And that's it for this video segment, and I'm looking forward to talking with you again soon.